Welcome back to the channel. Today we're going to look at compositions of functions. And our objectives today is first of all going to define what compositions of functions are and then look at some examples. We'll talk about how to evaluate compositions of functions and then get into finding the domain of a composition of functions, which might not be what you think. And then at the end, we're going to finish up by talking about how we can decompose functions. Let's first define what a composition is. The composition of two functions, f of x and g of x, denoted by the expression f composite g. That little circle there is the symbol for the composition. F composite g of x is equal to f of g of x. We can think of a composition of two functions as placing one function inside of another function. First of all, let's take a look at the basic steps for finding the composition of functions. First, we want to replace x in the outer function with the inner function g of x. And then from there, we just simply evaluate and simplify. Now, there is quite a bit of algebra that's involved in doing these steps, but it's not that complicated. Suppose we have the function f of x equals 3x minus 4, and g of x equals 2x squared minus 7x plus 5. F composite g of x is equal to f of g of x. Now g of x, of course, is 2x squared minus 7x plus 5. So we can plug that in for g of x. We do our first step, replace the x in the outer function with the inner function g of x. So the x that we have here, we're going to replace with all of g of x. So this entire expression, we'll plug that in for x. In so doing that here, we end up with, instead of 3x minus 4, we have 3 times 2x squared minus 7x plus 5 minus 4. So just replacing the x with that entire expression. All we need to do at this point is evaluate this and simplify. So we can distribute the 3 to give us 6x squared minus 21x plus 15 minus 4. And then from there, combine the like term to get our final result of 6x squared minus 21x plus 11. Let's take a look at another example. We're going to look at the same two functions, but now we're going to switch the order of the function. So instead of f composite g of x, we're going to look at g composite f of x. So here we have g of f of x. So that means we're taking g of what f of x is, which is 3x minus 4. So then we're going to replace the x once again in the outer function with the inner function. Now here, the outer function is g of x. So everywhere that we see x in g, we're going to replace with the entire expression 3x minus 4. So we'll place that here, and we're also going to place that expression where we see x here. So instead of having 2x squared minus 7x plus 5, we now have 2 times 3x minus 4 squared minus 7 times 3x minus 4 plus 5. So the next step here is to evaluate this and simplify. Here, the first thing we'll do is we'll take 3x minus 4 squared, that's the exponent. So remember that 3x minus 4 squared is 3x minus 4 times 3x minus 4. You follow that thing out, that part will give you 9x squared minus 24x plus 16. So we'll multiply that by the 2, bring everything else down, and now let's go ahead and multiply. So we distribute the 2 to get 18x squared minus 48x plus 32. Distribute the negative 7 to get minus 21x plus 28, and then bring down the 5. Combine the like terms to get our final result of 18x squared minus 69x plus 65. Now, one thing that you'll probably notice is that this isn't the same answer that we got when we did f composite g of x, and that leads us to one of the first things that we want to be mindful of when doing compositions of functions, and that is that the composition operation is not commutative. That's just saying that f composite g is not going to give you the same result as g composite f. So now let's take a look at a little bit of a challenging example here. Here we have the function f of x equals x plus 5 over 2x plus 1, and g of x equals 3 over x minus 4. When we take the composition here, f composite g of x equals f of g of x. When we take the composition here, f of g of x, We're taking f of whatever g of x is, which in this case is 3 over x minus 4. F of 3 over x minus 4, understand what this means? Everywhere we see x in f, we're going to replace that with g of x. So in these two places where we see x in f of x, those are going to be replaced with 3 over x minus 4. And so that would look something like this. Instead of x plus 5, we have 3 over x minus 4 plus 5. In the denominator, which was 2x minus 1, this will be 2 times 3 over x minus 4 plus 1. So here we have a bit of a mess. We've got fractions inside of fractions. Now, before we look at trying to clear this out, let's do a little bit of cleaning up here. In the denominator, we can multiply the 2 by the 3 over x minus 4 by multiplying 2 times 3. And I can take out the parentheses too in both cases. So we have 3 over x minus 4 plus 5 all over 6 over x minus 4 plus 1. We want to clear out the smaller fractions inside of this big fraction. The most common way that we do that is by multiplying the top and the bottom by the common denominator of all of the small fractions. Now in this case, we only have a denominator of x minus 4 for the small fractions, and so we'll do just that. Multiply both the top and the bottom by x minus 4. What this means is that we're going to be multiplying both of the terms by x minus 4. So x minus 4, we're going to multiply this by 3 over x minus 4, and also multiply x minus 4 by 5. And then likewise do the same thing in the denominator. So each of those terms, or those groups, will be multiplied by x minus 4. So that will look something like this. What we notice then is that for the first group, 3 over x minus 4 times x minus 4, the x minus 4 cancels out. It cancels out the denominator, leaving us with just 3. And the same thing happens in the large denominator. The x minus 4 cancels out there, leaving us with just 6. So if we take this expression, 3 plus 5 times x minus 4, and we'll go ahead and distribute the 5 on top and the 1 on the bottom, that will give us the expression 3 plus 5x minus 20 over 6 plus x minus 4. Combine like terms to get our final result of 5x minus 17 over x plus 2. Sometimes when you're working on homework or practicing these problems, you'll see rational expressions being used. So just be very careful, and you can utilize this trick of clearing out those smaller fractions in order to simplify the expression. Let's talk about evaluating a composition of functions. Now, there are two ways that we can go about evaluating a composition of functions. One is to find the composition first, calculate that, and then plug in the value of the x that we want to evaluate the function. Or we can evaluate the inner function completely, then take that result and plug it into the outer function. So let's say, for example, we want to evaluate f composite g of 5, and we're going to use the same two functions that we did before. F of x equals x plus 5 over 2x plus 1, and g of x equals 3 over x minus 4. Remember that f composite g of x, that was 5x minus 17 over x plus 2. So with the first method, we find the composition first, and then we evaluate. F composite g of 5, we just replace the x in the composition with 5. That gives us 5 times 5 minus 17 over 5 plus 2. We simplify that. 25 minus 17 over 7. We have a result of 8/7. In the second method, we kind of work from the inside out. So from this, we use the fact that f composite g of x, by definition, is f of g of x. Here, we're going to evaluate this for 5, so we're going to find f of g of 5. When we plug 5 into this function, into g of x, g of 5 is 3 over 5 minus 4, which is 3 over 1, which gives us a result of 3. We are finding then f of 3, since g of 5 is equal to 3. And then we take the number 3 and plug that into the function f. In so doing, we have 3 plus 5 over 2 times 3 plus 1. That's 8 over 6 plus 1, which gives us 8/7. We get the same value, which should come as no surprise. Benefits and drawbacks. The first method obviously takes fewer steps on the back end, but it does require that you go through all of the work of finding the composition, which, as we saw for this particular example, did take quite a few steps for us to complete. If you're going to evaluate the composition of functions for a number of different values, the first method is probably a good idea. However, if you're just doing one random evaluation or one specific evaluation of a function, the second method might be more beneficial. Let's take a look at another example. I'm going to use the same functions, but now we're going to evaluate f composite g of 4. I want to do one more example to point out something that we have to be careful about when it comes to compositions of functions. Let's evaluate f composite g of 4. So with the first method, if we find the composition first and then evaluate, that becomes 5 times 4 minus 17 over 4 plus 2. This gives us a result of 20 minus 17, which is 3, 4 plus 2, which is 6, which is equal to 1/2. If we use the second method here, where we do f of g of 4, g of 4, that's 3 over 4 minus 4, which is 3 over 0, which is undefined. So we can't even, if we do the second method, we basically run into a wall because we get an undefined result when we evaluate the inner function. Is the composition at 4 undefined, or is it going to be equal to 1/2? The correct answer here is going to be that this is undefined. Why in this case is it undefined? Because when we found the composition first, clearly we were able to plug 4 in. The answer lies in the fact that the composition, how did we get the composition? We got the composition by taking f of g of x. So we plug the function g of x into the outer function so that any restrictions that we have on g of x are going to be carried along into the composition. So if any value that is outside of the domain of the inner function also has to be outside the domain of the composition. So if we evaluate the compositions of functions, we want to make sure that we take into account the domain of the inner function as well as the domain of the overall answer. So the domain of a composition of functions will consist of the intersection of the domain of the composed function and the domain of the inner function. The domain of f composite g equals the domain of f composite g with the intersection of the domain of g, or the domain of the inner function. So let's find the domain of f composite g for this same example. It should be easy to see that the domain of the composition would be all real numbers except -2, because that's the only value of x that would make the denominator 0 and make that result undefined. The domain of g, 3 over x minus 4, is all real numbers except 4. So for the composition, the domain of f composite g will be all real numbers except -2 and +4. So we take into account the restrictions not only of the expression that we get from the composition, but also the inner function. Now let's finish this out by talking about the decomposition of functions. In some cases, we may be able to take a function and break it up or decompose it into two functions whose composition is equal to the original. Typically, in these instances, we look for a function that has an inner part and an outer part. So let's say, for example, we want to find two functions, f of x and g of x, such that h of x is equal to f composite g of x. So let's say our function is h of x equals the square root of 4x plus 3. Now in this function, you can kind of see that there's an outer part and an inner part to it. All right, we have a square root over this entire expression 4x plus 3. So this expression we can break up in terms of an inner function and an outer function. Now the inner part of this function would be 4x plus 3. So in this case, that would be our g of x. Our outer function is the square root part. So we'll refer to that as the square root of x, and that will be f of x for us. And if we were to take the composition of these two functions, f composite g of x, which of course is f of g of x, this would be f of 4x plus 3. And remember, we replace the x and f with the entire expression that's g of x. So that would give us the square root of 4x plus 3, which of course is our original function h of x. Now, one of the interesting things about the decomposition of functions, now there is an alternate way that we could solve this problem. So taking the same problem, h of x equals square root of 4x plus 3, if we let the inner function be 4x and the outer function f of x be the square root of x plus 3, it's f of g of x, that's going to be f of 4x, and we replace the x in f with 4x in this case, which will give us the square root of, instead of x plus 3, it's the square root of 4x plus 3, which is our original function again, h of x. So one of the things about the decomposition of functions is that it's not unique. So there may be multiple ways of breaking up a function into two functions that gives us this original. When you're doing a decomposition of functions, usually it's going to be fairly obvious what you're going to have for an inner function and an outer function. All right, so that's going to wrap it up for today. If you found this helpful, please feel free to leave a like. If you have any other questions, you can leave questions in the comments, or if there are any other topics that you'd like for me to cover, please leave those in the comments as well. You have a good day. See you later.